Yes, good morning. So, from the previous lecture, we analyzed that the common source amplifier without source resistor. Now, in this class, let us see the same common source amplifier but including the source resistor. Okay, so when this is almost similar to common emitter amplifier with the emitter resistor. Okay. So with the including of emitter resistor, what is the advantage? The input impedance is increased very high. Okay. Similarly, here also, let us see the analysis. Okay. The slide representing the common source amplifier with a source resistor. So as usual, the MOSFET is for the amplification purpose. R1, R2 and RS provides a biasing circuit with the help of VDD. RD is the load resistor, its action, and also it acts as the current limiting resistor. And whereas the coupling capacitor purpose is, to allow only AC component to the amplifier and it blocks any DC. Whereas VI is the signal source. Right? So that is about the description of this common source amplifier including RS resistor. So before going to analyze this circuit, first of all you need to convert it into equivalent model. Okay, what is the equivalent of MOSFET between gate to source? It is represented as open circuit because the gate offers very high input impedance, or if you take the MOSFET structure, the gate is separated from the substrate by an insulating material, right? But whereas at the source to drain, it is represented by a current source with the value Gm into VGS because the output current depends on the input voltage VGS, right? And uh, let us see now in the equivalent model. This is the diagram you can plot. This part is because of MOSFET. MOSFET is replaced by its equivalent circuit like this. And from source to ground, there is a RS resistor. Its location is as it is. And in the equivalent circuit, the VDD supply is short circuited. The VDD supply wire is connected to ground. Therefore, R1 comes in parallel with R2 and the RD resistor is between output to the ground. As usual, at the input, the source voltage, that is VI. First of all, let us see the voltage gain derivation. The voltage gain means output voltage divided by input voltage. Here output voltage is V0, input voltage is VA. So AV equal to V0 divided by VA. Okay. First of all, I'm looking what about the output voltage? What about the output voltage? From the diagram, the voltage across RD is the output voltage. The voltage across RD is the output voltage. But how much is the voltage drop across RD? How much current is flowing? That is GMVGS. Okay, GMVGS or GMVSG. Because the polarities are source is positive, gate is negative. That's why it is represented as VSG and the current direction is upward direction. So the output voltage is GMVSG into RT. GMVSG into RT. Okay. Where VSG is, it is derived from the input. It is derived from the input. If you see, the Vn is by writing the KVL equation at the input side. Therefore, Vn equal to minus VSG Vin. This is the Vin. This is the Vin between this point to this point. That Vin is VSG plus the drop across RS. How much is the drop across RS? Minus GM VSG into RS, because this is the current flowing through this resistor. That's why minus GM VSG RS. Therefore, from this the VSG equal to minus VI divided by 1 plus GM into RS. Right? Now substitute this VSG in the output voltage equation. Hence, we can get the voltage gain as AV equal to V0 divided by VI, that equal to minus GMRD divided by 1 plus GMRS. Okay. Next, coming to input and output impedances. So, if you see the input impedance, that is before the biasing circuit, the input impedance is R1 parallel R2. R1 parallel R2, because the VGS is in open. Okay, if you look the resistance here, it is R1 parallel R2. And coming to output resistance, okay, for calculating the output resistance, all the independent sources must be 0. That is, Vs is 0. So when Vs is 0, the VGS becomes 0. Hence, when VGS is 0, the current source, the dependent current source value is 0. Means it acts as an open circuit. Therefore, the R0 is equal to just RD. R0 equal to RD. These two similar to whatever we derived in the common source amplifier without source resistor. Okay. Same way here also you can represent. You note down those two also. And the next amplifier is, okay, anyway, okay, let us see the same amplifier in the same class. Same amplifier means the next type of amplifier is common drain amplifier. This is the common drain amplifier, right? In this common drain amplifier, you know, common drain means the input is at the gate, the output is from the emitter, whereas the drain terminal is at the ground potential. Sorry, not emitter. It is source, from the source. Okay. If you consider the output from the source and input at the gate, that is rated as the common drain amplifier. Even though it looks like common source, since the output is taken from the source terminal, therefore it is a common drain amplifier. It is a common drain amplifier, right? Okay, here also the circuit description is the MOSFET is for amplification purpose. R1, R2, RS provides biasing with the help of VDD, and RS also acts as the load resistance. CC is the coupling capacitor which couples only a signal to the amplifier stage. Okay, and VI is the signal source. Now for analysis, first of all you need to convert it into small signal equivalent model. Let us see. This part is, instead of MOSFET, it is replaced with the equivalent circuit. The equivalent circuit now includes R0 also. R0, why R0 is included means the channel length modulation is considered. Okay, and RS is between source and ground as it is, whereas R1 comes in parallel with R2. Okay, now for our convenience, it is I am again modifying like this, rearranging this one like this. Okay, both are same circuits. So to avoid the confusion while analyzing input impedance, output impedance, etc., I am representing this circuit is like this. Okay. Now from this, as usual, first of all, I'm going to derive the voltage gain. For that, what is the output voltage you need to see, because the voltage gain formula is output voltage divided by input voltage. If you look in every analysis case, first one, we are deriving the voltage gain. We are deriving the voltage gain, that is the ratio of output voltage divided by input voltage. Okay, and here the output voltage is the drop across parallel combination of RS and small r naught. RS and small r naught, right? What is the drop and how much is the current flowing through this resistive network, that is GM VGS. So therefore the output voltage V naught equal to GM VGS into RS parallel R naught. RS parallel R naught. And now from the input side you need to find out the VGS value. VGS, right? Okay. So now what is VGS here? The VGS is for VGS. Write down in KVL equation here. So VIN equal to VGS plus V naught. VGS plus V naught, right? And V naught already derived as like this. This one, substitute that value here. From this, the VGS you can write as like this: VGS equal to Vin divided by 1 plus GM RS parallel R naught. Okay. The same equation you can also write like this. Okay. Now substitute this VGS voltage in the output equation, in the output V naught equation. Therefore, the voltage gain is like this. The voltage gain is again the Vin in terms of Vi you have to write. Why? Because the voltage gain is V naught by Vi. V naught by Vi. Okay. So from the input side, if you see in this voltage divider circuit, Vin is applied voltage Vi into this parallel combination of Ri, R1 and R2 is Ri, right? So therefore Ri divided by Ri plus RSI. Okay, that is the Vin. Then substitute this Vin in VGS and then substitute VGS in the V naught equation, so that you can get the gain AV equal to V naught divided by VI, that equal to GM into RS parallel R naught divided by 1 plus GM into RS parallel R naught into Ri divided by Ri plus RSI. Okay, where how much is the Ri? Ri is the parallel connection of R1 and R2. Okay, that is the input resistance. So this is the voltage gain, and now coming to input resistance, what I said previously, it is R1 parallel R2. And for output resistance, as usual, independent sources must be 0. Independent source must be 0 means the Vs becomes 0 here, and a test voltage Vx has to be connected at the output terminals. Right? So the output resistance is now defined as Vx by Ix. Okay, the output resistance you can define as Vx divided by Ix. Okay, so to derive it, it is better to write the KCL equation at the output node. Okay, what is KCL equation at output? The output means at the source terminal, Okay, that is Ix plus GM VGS equal to, these two are the incoming currents. That equal to outgoing currents are Vx divided by Rs plus Vx divided by R naught. Okay, so this is the equation, KCL equation at source, right? And now here in this network, the VGS is, because there is no input source, therefore the VGS is equal to minus Vx, right? If you observe here, VGS is equal to minus Vx. Okay, substituting that in this equation, and taking the Vx as common, the current equation is like this: Ix equal to Vx of Gm plus 1 by Rs plus 1 by R naught. Therefore, Ix by Vx is equal to inverse of the resistance, that is output resistance 1 by R naught. Okay, I by V represents the 1 by R naught. So that equal to Gm plus 1 by Rs plus 1 by small R naught. Hence the output resistance R naught is 1 by Gm parallel Rs parallel R naught. Okay, like that the output resistance is derived in common drain amplifier, right? Okay, so every day you need to practice all these derivations. Okay, because all are quite same. All are quite same. Thing is, after plotting amplifier circuit properly, you need to convert into equivalent model. Okay, then it is very easy. If you observe in every analysis, the flow is same. The flow is same. Thing is, you don't confuse. If practice gives, and practice makes easy. Practice makes easy here. Okay, thank you.